This one. Okay. All right. Sorry, I was a couple minutes late there. I got 85% of the way here and then realized I didn't have my silly microphone. So, but anyways, what I want to start with today is something kind of fun, I hope. It'll be quick, but hopefully kind of neat. So, okay, well, the first thing I want to do is I want to tell you that assignment 2 has been posted if you didn't know already. And so the due date is Friday of next week. That is the day before the reading break starts. So please submit those assignments. I don't want to collect late ones for, when we're on reading week. So get this thing to me by Friday of next week. All right. Good. And then let me start this thing here. All right. That's good. Okay, good. Now we're all set. So part of what I did last weekend is I made a couple little simulations of Brownian motion. And so diffusion. So I'm going to open one of these and show you what it looks like, I hope. All right, good. So these are available on the course website. You can open these yourselves. And if you wanted to, I don't know, play with them or change something about them, that's all possible. This first one, what it's going to try to do is it's going to try to simulate Brownian motion by making use of the binomial distribution. So it's exactly like the stuff that we've been talking about in class, except it will be a two-dimensional version. We've been talking about like a drunk starts at a stop sign and they take steps left or right. So here, these are particles. They're going to start in the center of some kind of chamber, and they can go left or right or up or down. And so if they go left or right, it's 50-50 chance. Same thing, up and down is 50-50 chance. And what we're going to do is we're going to place 10,000 particles. So here it is, E1 times 10 to the minus 4, 1 times 10 to the 4 is 10,000 particles. And we're going to watch them as they take 500 steps of Brownian type motion. And so this is also analogous to what we talked about before. You have a beaker of clear water, then you take an eyedropper and you place 1 drop of food coloring in the center and you watch the thing diffuse out. So that's the same thing. Or if you want to think of it this way, you can take 10,000 drunks, put them at the stop sign, tell them go, and then see where they are after 500 steps. Okay, so what we're going to see is a couple of plots like this. So I'll run the simulation. We'll see this. This is 0 to 1 in the X direction and 0 to 1 in the Y direction. So we have this square chamber. And you see this little faint blue or cyan dot. That's the initial position of all 10,000 particles. So they all get placed at this exact same spot. And then we'll watch them move around. At the same time, what it's going to do is it's going to count the number of particles as a function of height. And so we'll have these like 20 strips or so, and it'll count how many particles there are at different heights the whole time the thing's running. And so initially, we'll only have particles at a height of 0.5. So there'll be a large number of counts right here, and then there'll be 0 counts everywhere else, and then we'll watch the thing evolve. Okay, so let's try it. Hopefully this works. Uh-oh. It's not working. Why isn't it working? I'm gonna fix it. Okay, so I think it's not working because I maybe let's see. Oh, whoops. Okay, so let's try this again. All right, and I'm pretty confident that I can get this thing working because I ran it before class. And here's the issue, is this thing here. Okay, good. So all the particles started here, and then they just randomly move out. This is kind of nice, like this kind of spread is sort of a measure of the standard deviation, and it's also like a measure of the width of this kind of peak. So you can see the standard deviation evolve as this thing's running. I'm also calculating the average positions at every step, and you can see that it's always 0.5. So we have, even though these things are spread out, if we calculate the average position, it's always 0.5, because whenever we have one over here, there's one over here that when you add them up, they average out to be in the middle. Yeah.
If you were to start them at a position that was not the center, would they still have that spread evenly at 0.5, or would it be at that point?
Well, it would be at whatever point you started them at. Yeah, yeah. And so if we let this thing run long enough, which we will do, what we'll eventually achieve is a uniform distribution of particles. So, you know, it's still a little denser in the center, and you can see that in this plot here. This can run up to, I think, 500 steps. And so by the time we get to 500 steps, this should look like a uniform distribution of particles, and this will be a flat distribution of counts. So the tails are coming up, and the peak, which is at 800 now, will come down. And so we'll just watch this for another minute or so. If you're interested, I'm not going to run it here, but I also made like a 3D version of this. And so you place particles at the center of a cubic volume, and then they spread out spherically, and you can see that sphere grow as the number of steps increases. And you can see this was at 800, now it's down below 700, and it'll keep coming down, and the tails will keep coming up, and we're going to get this kind of flat distribution. I will show you one more here. And while this is running, I'll set up the second one. In the second simulation, what we're going to do is we're going to have the same 1 by 1 box of particles, but we'll start with all of our particles distributed uniformly. So it's like this one has been running for a long time, and then we have this completely random distribution of particles. In the second simulation, what we're going to do is we're going to say that it's more likely for a particle to move down than to move up. And the way we're going to implement that is, if you look in the code here, somewhere there is binomial distribution. And so here's the binomial distribution, and this is the probability that a particle moves, say, to the right, it's 0.5. This is the probability that a particle moves up, it's 50%. So what we'll do in the second simulation is we'll say that the probability of a particle moving up will be something like 0.25, and the probability that it moves down is 0.75. And what that's designed to do is it's designed to simulate gravity. So in a real suspension of particles, if you do the Brownian motion experiment, particles are more likely to move downwards because of that gravitational force. And what that leads to is a distribution in the density of particle number that changes as a function of height. And that's the type of measurement you do on day 2 of the experiment. Okay, and so now you can see the particles are more or less evenly distributed. And when we look at the particle number as a function of the height, it's flat. Nevertheless, when we look over here, the average position is still 0.5 in the X and Y directions. And there's some standard deviation that has grown, and it grows as time evolves because our particles spread out further and further and further. Okay, and then eventually, I guess this will eventually reach, I think, 499, and it'll stop. And then we'll just have this kind of uniform distribution of particles. Okay, now I want to show you the second one. Because the second one is also relevant to your homework. And it's relevant to day 2 of the Brownian motion lab. So we'll let this thing load up, and then I will show you. Let's see here. This code is very much similar to the previous one. So here it is, the probability that a particle moves up is 25%, and so therefore 75% chance that it moves down. And so what we're going to do is, here, this is what it's going to look like at the end. The blue or cyan points is the initial starting position of all the particles. And so they're just randomly placed in this 1 by 1 square. And then the orange ones are going to be how the particles evolve with time. And so at the end of the simulation, a lot of them have settled down to the bottom. The way this one will work is if a particle reaches the bottom, we'll just keep it there. So we won't let it go past the bottom. Just another thing that these simulations do is a particle could randomly move past x equals 0. So if the position becomes negative, what we do is we just have that particle reappear close to the right-hand boundary. Okay, so let's run it and let's see what happens. Okay, so here we are. The orange ones started where the blue ones are. The blue ones aren't moving, they're just static. Here is the distribution of particles as a function of height. It was initially flat, but as time evolves, we lose particles from the top region and we gain particles in the bottom region. This is actually plotting the ln of the number of counts. And what we're going to find is that this is eventually going to be a linear plot. It's already looking pretty linear. And because it's the ln of the number of counts, what this tells us is that the density of particles is evolving exponentially. So there's exponentially more particles near the bottom than there are on the top. And so we get this kind of linear thing. And that's it. This one stops after 100 steps. So what you do in day 2 of the Brownian motion experiment is we set up this slide, we let it sit for at least 12 hours so that we achieve this exponential distribution of particles, and then you count the number of particles at different heights along this distribution, and the ln of those counts as a function of height should be linear. That slope has Avogadro's number in it. Okay, so in the first question of your assignment, number 2, is to try to analytically solve for this result, not using a simulation. All right, good. Any questions about these? No. All righty. So let's go share this screen, start. And let's see if we can find the right notes. Maybe this one. Yes. So binomial distribution, there it is. We wrote it down. And what I want to do is today we watched the simulation, and what we're going to try to do today is we're going to try to derive the Poisson distribution. And the way we're going to do it is we're going to start with the binomial distribution, and we're going to consider some special cases of the binomial distribution. And from there, we'll make our way towards this so-called Poisson distribution. Okay, so the Poisson distribution is a special case of the binomial distribution. Okay, the special case is that the mean mu is much less than the number of trials. So this is the mean. This is the number of trials of an experiment. And we know for the binomial distribution, the mean is equal to n times p, right? So since mu is equal to np for the binomial distribution, our condition here is that mu, or np, is much less than n, and then you could divide by n, and you could say p is much less than 1. So that gives kind of like a little more intuitive interpretation of what the Poisson distribution is. It's the distribution when the probability of success is very small. So the binomial distribution approaches the Poisson distribution when the probability of success p is small. Okay. So before we do the derivation, let's just think of like a possible situation in which you might encounter this scenario. And so an example is in counting experiments. So we have an experiment in the 3rd year lab, Physics 331, in which you watch for muons decaying. And so the idea is you stop a muon in a piece of plastic, and it starts to counter, and then you wait a short amount of time, and if that muon decays, you stop your stopwatch or you stop the counter, and that gives you the lifetime of that one muon, and then you want to do it over and over and over again so you can get the average lifetime of the muons. But it turns out that most muons will go straight through your plastic. They don't stop, and so they start a stopwatch, but then you never see the decay. And so the probability of successfully observing a muon decay is very low. So that means you have to run the experiment for a long time, and that's what we do. So the example is we count the number of muon decays in time interval delta t, and we repeat many times. We usually get no decays for a short delta t, and so that means the probability p for observing a muon decay is small. Okay, so the properties of the Poisson distribution that we derive in physics are most applicable to these counting type experiments that occur all the time in like particle physics. Okay, so let's start with the binomial distribution. The binomial distribution for X successes when the probability of success is P, I think we usually do it this way. When we run N trials of an experiment and the probability of success is P, was N choose X, which we can write as this combination of factorials. And then it was P to the X times 1 minus P to the N minus X. All right. So all I'm going to do is I'm going to rewrite this exact same expression. I'm just going to break up some of the factors. So I'm not making any changes right now. I'm just rewriting this thing. So we'll start by isolating the 1 over X factorial. And then that will leave us with a N factorial divided by N minus X factorial. And then we'll have the P to the X. And then we have this 1 minus P to the N minus X. I could write that as 1 minus P to the minus X times 1 minus P to the N. Okay, so I've just broken this up in some funny way. And we're going to work on these different factors in this product. So I'm going to call this N factorial over N minus X factorial. I'm going to call that factor 1. We'll take the 1 minus P to the minus X, and we'll call that factor 2. And we'll take the 1 minus P to the N, and we'll call that factor 3. So the idea is we're going to make some approximations. And we're going to make some approximations for these 3 different factors, and then we'll bring them all together, plug them back into this expression, and that will be our derivation of the Poisson distribution. Okay. So factor 1. All right. So we have N factorial over N minus X factorial. All right. So N factorial, you know, is N times N minus 1 times N minus 2 times N minus 3, and so on, times N minus X times N minus X minus 1 times N minus X minus 2. All of those factors at the end are going to cancel with this N factorial. So in fact, we could write this as N times N minus 1 times N minus 2, and so on. And then we're eventually going to get to N minus X plus 1. And then we'll have N minus X. And instead of writing N minus X times N minus X minus 1 times N minus X minus 2, I could leave this last thing on the tail as N minus X factorial. And then, of course, that's divided by N minus X factorial. And those are going to cancel. Okay, good. So now we haven't made approximations yet. This is still exact. We are about to make an approximation. We said the probability of success is very low, and X is the number of successes. So that means X is a small number compared to N. So when I do N minus X plus 1, it's N minus a small number plus 1, which we're going to approximate as just being N. So if N is like 1,000,000 trials and there was 100 successes, we're just going to say 1,000,000 minus 100 plus 1 is still 1,000,000. And 1,000,000 minus 2 is still 1,000,000. And 1,000,000 minus 1 is still 1,000,000. Okay, so since P is very small, that means X is much less than N. We have few successes. And so therefore, we're going to say n minus 1 is approximately n, and n minus 2 is approximately n. And we keep going, and we would get to n minus x plus 1 is approximately n. And so therefore, our first approximation for this ratio of factorials is just a bunch of factors of n, and if you count them, can anyone, how many are there? So there is 1, 2, so let's see, starting from 0, we go n minus 0, and then minus 1, minus 2, and then minus x plus 1. So there are a total of x factors in this combination, because we have the minus x plus 1, or let's say that's x minus 1, but then we have where we have x equals 0, so we have to add 1 for that case, and so it ends up being x factors of n. So there are x of, whoops, sorry, x of these factors. Okay. All right. So therefore, when we see this n factorial, n minus x factorial, and then if we multiply that by p to the x, all of this is n to the power x. So this is equal to n times p to the power x. But n times p was just the average value. And so this is equal to mu to the power x. Okay, so that's our first results. When we go back over here, we're going to replace all of this with mu to the power x. Okay, so that's one of them. Let's try the second factor. The second factor was 1 minus p minus x. This one is pretty trivial. So if p is very small, what's 1 minus p? 1, okay? And then what's 1 to the minus x? Just a 1, okay? And so all of this thing is just going to be approximately 1 to the minus x, which is just equal to 1. Okay, so that one's not very fun, but it's easy. Okay, so this thing here is just going to go away. It's just going to be a 1. And so then we have only this third one to do, 1 minus p to the n. All right. So 3 is 1 minus p to the n. Okay, so we've used this already. We know that p times n is equal to mu, and so therefore n is equal to the mu over p. Okay, so 1 minus p to the n is approximately equal to 1 minus p to the mu over p. Now, what you might do is you might say, well, hold on, what the hell are you doing here? We just said 1 minus p is approximately equal to 1. So why aren't we doing the same thing here? Well, the idea is that this is 1 minus p to a small number, because we had a small number of successes. So if you take, I don't know, 0.95 and raise it to a small power, it's still the number that's close to 1, like 0.95 squared is still not that far from 1. But if we do 1 minus p to a large power, then what we end up with is something like 0.95 to like 100, and then that's not so close to 1 anymore. Okay, so the difference is large power, small power. That's why we're doing a different approximation. Okay, so this thing could be written as, I'm gonna write it in some kind of silly way. 1 minus p, that's normal. But what I'm gonna say is that that's to the power p. And then we're gonna raise all of that to the power mu. So that's, this first step was an approximation. This is still exact. It's just kind of a funny way of writing this thing. Okay, so my claim is the following. I claim that the limit, in the limit that p goes to 0, so a small probability, we're going to have 1 minus p to the power of 1 over p is equal to 1 over e, where e is Euler's number. Right, it's what's e to the 1 is like 2 point, I don't know e very well.
2.71828.
Yeah, 1828. Okay, there we go. Okay, so what I want to do is I want to prove this, and you may have seen it before. It's actually not that hard to prove. So let's try it. So there's our claim. So here's our proof. Before we do the proof, what we're going to do is we're going to say, if this is true for small p, we assume that our Poisson distribution was the small p limit of the binomial distribution. So then everything in the square brackets here is going to be 1 over e, and we're just going to raise that to the power of mu. That's all we're going to do. So let's see if we can do the proof. So we're going to start with, let's say y is equal to 1 minus p to the 1 over p power. All right. So if that's true, then the ln of y is equal to the ln of all of this, but I could write that as 1 over p ln of 1 minus p. Okay. All right, so then the limit that p goes to 0 of the ln of y is approximately, what's an approximation for ln of 1 minus a small number? Well, so the 0th order approximation, you're right. If I just ignore the p, I'd have ln of 1, and that would be 0. And that's correct. What if I wanted a slightly better approximation? The ln of 1 minus p when p is small. What's that? It's minus p. So recall that the ln of 1 plus x is approximately just x when x is much less than 1. Okay, if you wanted to prove that, all you would do is you would just write the Taylor series expansion for the ln of 1 plus x, and you would keep only the first term, and it's just x. And if this is a minus sign, then you get minus x. Okay, so you can do this using Taylor series. Okay, so then we have 1 over p times minus p, which is equal to minus 1. And so now we just take the exponential, exponentiate both sides, and so therefore y is approximately equal to e to the minus 1 when p is small. Okay, and since y was this thing at the top, we would have that 1 minus p to the power of 1 over p is approximately 1 over e when p is small. And so that's our proof. Okay, so then what we're going to do is we go back to this expression, 1 minus p to the power n. 1 minus p to the power n is equal to, what was it? It was 1 minus p to the 1 over p to the power mu, was it? Yes, it was. And so that's going to be approximately 1 over e to the mu. And so that's equal to e to the minus mu. All right, good. So that's our third approximation. That final factor is e to the minus mu. So over here, we're going to say that this thing is e to the minus mu. All right, and then we've got everything we need. And so we're going to go and say that in the limit that p goes to 0, our binomial distribution for x successes out of n trials when probability of success is p is approximately equal to 1 over x factorial. We had that out front. We didn't do anything to that one. But then we had a mu to the x for our second approximation times p to the power x, right? So we had, remember our first approximation was n to the x, and then we took that and multiplied it by p to the x, and we said n times p was mu. All right, and then the one that we just did is e to the minus mu. And so then we can bring everything together and we can say, therefore, this is going to be a new distribution. This is our Poisson distribution, and it's going to be equal to mu to the x over x factorial e to the minus mu. So this is the Poisson distribution. And it is the p goes to 0 limit of the binomial distribution. Okay, good. Now, how are we doing time-wise? We got about 12 minutes. All right, so what I want to do is I want to check some properties of this Poisson distribution. And so one of the properties that we require, if this is going to be a probability distribution, it must be the case that the sum of all of the probabilities for different values of x must come out to be 1, right? So let's check the requirements that the sum of all of these probabilities for x equals 0 to infinity must be equal to 1. Okay, so the sum of x equals 0 to infinity of p x mu is equal to the sum of x equals 0 to infinity of our Poisson distribution is mu to the x over x factorial e to the minus mu. The sum is over x, and e to the minus mu has no x in it, so it's constant. It can come outside, and so this is e to the minus mu times the sum of x equals 0 to infinity of mu to the x over x factorial. What is, does anyone recognize this sum? Let's write out some terms. E to the minus mu. So x equals 0. Mu to the 0 is 1. X factorial when x is 0 is 1. So we just get a 1. Plus x equals 1. It's mu divided by 1 factorial. It's just mu. Plus x equals 2. Mu squared over 2. I'll write it as 2 factorial. It's just a 2. Mu cubed over 3 factorial. And you can see this is just going to continue. What is this? It's the Taylor series of? Yeah, it's e to the mu, exactly, that's right. This is the Taylor series of e to the mu. And so therefore, the sum of all possible outcomes for our Poisson distribution is e to the minus mu times e to the plus mu, which is just equal to 1. So that's kind of pretty. Makes you feel warm in the heart. Okay. So that works. So that's good. Another property we might look at is trying to find the mean of x. So what is the mean of the Poisson distribution? Okay, let's see. The average of x is the sum over all possible outcomes of x times the probability distribution. All right. So what are we going to get? X equals 0 to infinity, x times mu to the x over x factorial e to the minus mu. Okay, so what we'll do is we'll do this calculation in exactly the same way we did it for the binomial distribution. The first thing we do is just separate out the x equals 0 term. And that's just going to be 0 times some stuff. And so all of this just becomes, let's see, 0 plus, I'm going to put the sum over here, x equals 1 to infinity. E to the minus mu is still a constant. It still comes out beside the sum. And then we have x over x factorial. What is it? Mu to the power x. Okay. So this is e to the minus mu, sum of x equals 1 to infinity. X over x factorial is 1 over x minus 1 factorial, mu to the x. All right. So now what we're going to do is we'll take one factor of mu and put it over here. So it's mu e to the minus mu, sum of x equals 1 to infinity, 1 over x minus 1 factorial. What I'm trying to do is I'm trying to get all x minus 1s in here, and then we're going to make our favorite substitution. Y is equal to x minus 1. Okay, so then x average is mu e to the minus mu. Let's see. When x is equal to 1, y is equal to 0. So this is y is equal to 0. And then it still goes to infinity. And then it's 1 over y factorial, mu to the power of y. Okay. But we just did this thing. What is this? E to the mu. That's exactly what it is. So this is just e to the mu. It's the same Taylor series expansion that we just recognized in the above problem. And so e to the mu cancels with e to the minus mu. And we probably could have guessed this result, and maybe we should have tried, but we didn't. But x average is just equal to mu, which is the mean. Okay, so this is the mean of the Poisson distribution. Now, what I promised to do and then didn't do was to give you an assignment where you would calculate the standard deviation of the binomial distribution. So maybe I can make it up to you by having you calculate the standard deviation of the Poisson distribution. And so I think that's in fact exactly what I'm going to do. I will just tell you what the result is. So standard deviation. All right, so how much time? 5 minutes. That's kind of good. So we want to calculate sigma. I'll write down sigma squared. So sigma squared is the average of x minus mu squared, which is the sum of x equals 0 to infinity of x minus mu squared times the Poisson distribution. But that's the same thing as the average of x squared times the Poisson distribution minus mu squared. Okay, and so this is just the average of x squared. All right, so if you do this calculation here, what you'll find is that you could calculate a result for sigma squared. So homework number 3 when it comes out. It's not ready right now, but when it comes out, you will show that sigma squared is just equal to, let me see if I get the, yeah, that's right. That's what it should be. Sigma squared is just going to be equal to mu, or sigma is going to be the square root of mu. That's a little bit different than what we had for the binomial distribution. So the binomial distribution, we had an average value was n times p. And then we had the standard deviation squared, sigma squared, was n times p times 1 minus p. So they were independent from one another, right? Here, we have a standard deviation that's just given by the mean. Like there's no other factors in there. It's just the square root of the mean. So the Poisson distribution is characterized by a single, that's not how you spell single parameter mu. So the mean is just mu, and the standard deviation is the square root of mu. All right, good. So next time, what we'll do is I've got a couple of examples we can do where we can actually apply this. And I think what we'll try to do is we'll do some examples where p is really small, and we should be able to use the Poisson distribution, to calculate probabilities of different types of scenarios. But what we should find is that we should get the exact same results when we use the binomial distribution. Because remember, the binomial distribution is exact. The Poisson distribution is an approximation of the binomial distribution in the limit that p is small. So if we have problems with small probabilities of success, we should be able to use either the Poisson or the binomial distribution to get essentially the same final answers. Okay, that's where I'm going to stop for today. So we'll pick it up on Friday with some of those examples. All right, thanks very much.